Hello. We are going to discuss uh, Unit 1, Topic 14, Connecting Infinite Limits and Vertical Asymptotes, right? So we're still working with limits. We're just going to deal with infinities. I'm going to share some things about asymptotes you might already know to remind you of some quick ways to do it. And then I would like to expand that knowledge into some things you may not know. So below we have just some basic functions, trying to figure out where vertical asymptotes are for the following functions. The first one is just a reciprocal function. If you have this 1 over x, your asymptote is basically going to occur anywhere where the denominator is 0, right? Anywhere where you don't have a removable discontinuity. There's no way I can reduce 1 over x. So if I substitute the value of 0 in, it's going to make my fraction undefined. That's going to be a vertical asymptote. Okay. Furthermore, if you take a look at number 2, if you were to factor number 2, we're going to get a 2x. Let's see what we get here. It's going to be an x minus 3 and a 2x plus 3 all over x plus 3, x minus 3. The x minus 3's cancel. So then what I'm left with is a 2x plus 3 over an x plus 3. And your, I got too many parentheses here. Your vertical asymptote is going to occur when that denominator is 0, right? So it's going to be the non-removable discontinuity, or in this case, the infinite discontinuity, to use vocabulary from earlier lessons. So in this case, what value is going to make that denominator 0? Well, it's going to be x equals negative 3. All right. Now, I have a third function here. A lot of times, sometimes College Board will give you kind of abstract values, in this case, a, right? So what I want to do is I want to figure out what values of a are going to be a vertical asymptote, right? So we have to kind of factor this. And you have to be very careful because a lot of people think that the denominator here is going to be an x plus a, x minus a, but it's not, because it's not a squared. It's going to end up being x plus the square root of a and x. Oops, I wrote an a. It's going to be an x minus the square root of a. There's no way to reduce that. You can see that those are going to be two non-removable discontinuities, in this case, infinite discontinuities. So I'm going to have vertical asymptotes at a negative square root of a, and I'm going to have a vertical asymptote at a positive square root of a. Now, you also have the ability just to take the denominator and set it equal to 0. If you do that and solve it, again, that will give you where your vertical asymptotes are. But always look to simplify it first. Remember, remove the removable discontinuities, cancel those out, and figure out what's left. Okay? So just a little review of vertical asymptotes. So let's pair it with the idea of limits. So I have 3 graphs here, clearly with all vertical asymptotes, and I want to evaluate some limits that approach that asymptote. So as I approach a from the left, okay, what value am I getting closer and closer to? Well, my graph is going to go down forever, right? So for our purposes, now typically we would say that the limit does not exist here, but I want to be a little bit more descriptive. Because it's going down on the left, I'm going to say it's going toward negative infinity. Now, if you go to the right side of the asymptote, as I approach it from the right, it's going up forever, so that's going to approach a positive infinity. Okay, so it's pretty just visual, taking a look at it. From the left, as I approach A, is going to go toward positive infinity. From the right, as I approach A, is going to go to positive infinity. Now for the last function, as I approach from the left, I'm going to hit some sort of discrete value. I'm approaching this hole. Now I'm going to give it a value. I'm going to call it C. So it is going to approach the y value C, whatever that constant is. Now from the right side, as I approach from the right, that's going down forever. That's going to negative infinity. Now what I want to kind of show you is on h of x is a little different. you can see that only one side of my limit approaches infinity rather than two. That leads us into kind of a definition here. So if you have either the left or right side of a limit approach infinity, then you know you have a vertical asymptote. You don't need both. You just need one or the other. Okay? So what I want to do is I want to kind of talk about how to evaluate those limits and then what to do once we get those. All right? So if you take a look at number 1, I want to approach 3 from the right. Okay? Now, if you were to do a direct substitution here, I would get something like 2 over 0, which isn't very descriptive. So what I'm going to do is I'm going to kind of use a table of values. I'm going to kind of process this. I'm going to pick a value very, very close to 3 on the right-hand side. So let's say if I were to let x be 3.001, right? So that's just to the right of 3. I'm going to now have 2 over 3.0001 minus 3, which will give me 2 over 0.0001, which is going to be a very large number, right? So it's going to be what? 10th, 100th, 1000th. It's going to be something like 20,000, okay? Now, if I were to pick a number even closer to 3 on the right, 2 over 3.000001, right? Infinitely close to 3. I'm just going to get a smaller, I should say, decimal in the denominator, which is going to end up giving me a larger value, okay, and so on. So the closer that I get to 3 from the right, the larger the output of this limit will be. So you have to kind of think infinitely small. The way that I kind of process this is if I were to plug in a number 3 to the right, I'm going to get 2 over a very, very, very small decimal. And if you know anything about just numeric number sense, if you take a number and you divide it by an infinitely small decimal, that is going to approach the value of infinity. It's going to continually grow, okay? So let's take a look at number 2. Now, if I approach 3 from the left, right? So I'm going to let x, just so you guys can see, be something like 2.9999, right? So if I were to have that, I have 2 over 2.9999 minus 3, which gives me 2 over 0.0001, which would again be what? 20,000. Okay. However, it should be negative, right? If I do 2.99 minus 3, that's going to give me a negative decimal on the bottom. And if you take a positive value divided by a negative value, that's going to give you a negative output. So when I do this, and if you get incredibly small, the smaller that, or the closer that this gets to 3, the smaller my decimal in the denominator is going to be, but it's always going to be negative. So therefore, this limit is going to approach a negative infinity. Okay? So let's take a look at number 3. So if I approach negative 2 from the right, okay, now let's kind of work through this. If I approach negative 2 from the right, I'm looking at a number like negative 1.9999, okay? If I add that to 2, that's going to give me 5 over an incredibly small value squared, okay? Well, if you square that infinitely small value, I'm now going to have 5 over an even smaller value, which if you take a constant, divide it by an incredibly small decimal, and as that decimal gets smaller, this is going to approach a positive infinity. Okay, so that's kind of my logic. Now I can prove it numerically using a table of values, using your calculator. We can also logically think our way through this. Now, if I take negative 2 from the left, I'm going to take 5 over. Now, negative 2 from the left is something like negative 2.001. If I add 2 to that, I'm going to get a negative small value squared, which again is just going to give me a positive smaller value, because if you square anything, it turns positive, which will approach a positive infinity. Okay, so this is kind of how I logically work my way through it. All right, I know that there's asymptotes at those values. So now I just need to know, is it going to approach positive or negative infinity, or maybe even a constant for that matter? All right, if you take a look at number 5, you can always put it in your calculator, right? But how would you do number 5 without a calculator? That's a good question, right? How can I determine the vertical asymptotes without the use of a calculator? So I'm going to try to reduce this thing. So I'm going to say, okay, well, if I factor the first piece, x minus 5, x plus 2, all over x minus 5, right? Times the natural log, and I'm going to factor this, x plus 3, x plus 3, all over, I'm going to take out an x squared, x plus 3, right? You can see that we have a whole bunch of removable discontinuities, okay? So I have removable discontinuities at -5, at -3, right? So those pieces I'm not too concerned with. So I have an x plus 2 times the natural log of x plus 3. Now, I want to know what happens as I go to infinity for these. Where would these? Oh, I forgot over x squared. Sorry, guys. So where are my vertical asymptotes going to be? Well, I know without a doubt I'm going to have a vertical asymptote at 0 because it's going to make the denominator of my natural log 0, right? So I know that there is a vertical asymptote at 0. But the one that people always forget, if you guys know anything about a natural log, okay, there's a vertical asymptote. As you get closer and closer to the value of 0, you're going to have a vertical asymptote, right? So I am willing to bet when the numerator of a natural log is going to get closer to 0, I'm going to have an asymptote as well. So I'm going to have an asymptote at a -3. Now you can check this. If you graph it, double check. I bet you have those two vertical asymptotes. All right, so let's sketch a graph. Okay, so I said I was going to come back to one of these in a previous lesson. If I go from -2 from the left, right? So here's my -2. I'm going to approach the value of 1. So I'm going to start with an open circle from right now from the left. I kind of draw a little tail. I'm going to approach the value of 1. -2 from the right also approaches the value of 1, so I can do that. At -2, I'm going to be at 2. So I have a point here. At 1, as I approach 1 from the right, I'm going to go to infinity. As I approach, I did it from the left. You'll have to excuse the announcement in the background. Sorry about that, guys. Okay, as I approach 1 from the right, I'm going to go to infinity. As I approach 1 from the left, I'm also going to go to infinity. So I get a graph. I'm going to connect all the dots here, or pieces, I should say. Right? So I get a graph that looks something like this. You can make that right tail do whatever you want. Same thing with the left tail. There's no descriptors for the ends of my graph. But it might be in your best interest. I don't know, make a little dashed line, because we know that because I have a one-sided limit, or in this case, a two-sided limit, at x equals 1, I know will be a vertical asymptote. At -2, I do have a removable discontinuity. Okay? All right, so that concludes my lesson over vertical asymptotes. Just kind of a reminder, a vertical asymptote occurs when the denominator will be 0, but it will occur after you've reduced the function. Okay? Always reduce the function first, then find your vertical asymptote. Second, I want you to know this limit definition. If you have a one-sided limit approach infinity, that is your mathematical justification for a vertical asymptote. So if you have to justify why a vertical asymptote exists, you're going to use that limit notation. Okay.